Hi, Assalamualaikum. Welcome back to my channel Physics from 5 KSSM. Today we continue chapter 7 Quantum Physics on topic 7.1 Quantum Theory of Light. In this video, I will discuss 3 learning standards, explain wave-particle duality, explain concept of photon, solve problem using formula of photon energy and power. In my previous video, I have discussed that quantum of energy is discrete energy packet and not a continuous energy. According to Max Planck and Albert Einstein quantum theory, light energy exists in form of an energy packet known as a photon. The photon energy is directly proportional to frequency of light. So we can determine energy of photons by using a formula E equals to hf, where h is known as Planck constant. The value is 6.63 times 10 to the power of negative 34 joules second. So for this example 1, compare the energy of 400 nanometer and 750 nanometer of light photon. The value of 400 nanometer and 750 nanometer represent wavelengths of the light photons. The first value, 400 nanometer, we can label it as lambda 1, and the 750 nanometer, we can label it as lambda 2. As we know, light travels with speed of light in vacuum. C equals to 3 times 10 to the power 8 meters second to the power negative 1. By using the formula of energy photon, E equals to hf. But here we don't have the value of f, thus we need to calculate the value of f by using the formula C equals to f lambda. So from this formula, we get frequency equals to C divided by lambda. Substitute the frequency f equals to C divided by lambda into the photon energy formula. So we get E equals to hc divided by lambda. For wavelength, lambda 1 equals to 400 nanometer, we can calculate the energy of photon as E1. So E1 equals to hc divided by lambda 1. Substitute the value of Planck constant, which is h equals to 6.63 times 10 to the power of negative 34 joules second. C equals to 3 times 10 to the power of 8 divided by lambda 1, 400 nanometer, need to convert to meter. So 400 times 10 to the power of negative 9 meter. Okay, calculate for this value. We get the value as 4.97 times 10 to the power of negative 19 joule. For lambda 2, 750 nanometer, we use the same formula. So we get E2 equals to hc divided by lambda 2. Substitute the value of h, c, and lambda 2. Thus we get the answer for E2 is 2.65 times 10 to the power of negative 19 joule. Okay, go back to the question. Compare the energy of 400 nanometer and 750 nanometer light photons. As you can see from the value that we calculate just now, for 400 nanometer, we get 4.97 times 10 to the power of negative 19 joule, which is larger than E2. So from the value that we get here, what we can say about the light photons? The shorter the wavelength of light, the higher the photon's energy. Or, we also know that wavelength inversely proportional to frequency. Thus, we also can write this way: the higher the frequency of light, the higher the photon's energy. Wave-particle duality. Electromagnetic radiation such as light is said to have wave properties because it exhibits the phenomena of diffraction and interference, same as wave property. Objects like marbles are said to have particle properties because they possess momentum and kinetic energy and can collide with each other. In 1934, Louis de Broglie or de Broglie, a quantum physicist, had put forward a hypothesis stating that all particles can exhibit wave characteristics. However, it is experimentally difficult to show the wave characteristic of a particle like larger masses. Louis de Broglie predicted that the wave characteristic can be exhibited by lighter particles, for example electrons, means smaller mass of particle. Since the value of h is very small, particles of large masses will have de Broglie wavelengths which are too short to be detected. Therefore, the wave characteristic cannot be observed. Thus, for larger masses of particle, like the marble just now, it cannot show the properties of wave, as the wavelength that produced, that we call de Broglie wavelength, is too short to be detected. Now let's look at the formula about de Broglie wavelength. Lambda equals to Planck constant divided by momentum. Value of Planck constant is 6.63 times 10 to the power of negative 34 joules second. Is a very small value. Momentum of particle can be determined by formula P equals to mv. Once the particle has mass, it will have momentum. From the formula of wavelength de Broglie, lambda equals to h divided by momentum. Lambda equals to h divided by mv, where m is a mass of particle and v velocity of particle. When energy of photon is absorbed, electrons gain kinetic energy. Thus, kinetic energy also can be related to de Broglie wavelength. Let's discuss how to produce relationship between kinetic energy and de Broglie wavelength. From the formula of lambda equals to h divided by p, momentum p equals to mv. Thus, we get the formula lambda equals to h divided by mv. Kinetic energy of electron is equals to half mv squared. So, the value of v equals to v squared equals to 2k divided by m. means V equals to square root of 2k divided by m. Substitute velocity v into the formula of de Broglie wavelength. Thus lambda equals to h divided by mv. Thus equals to h divided by m square root of 2k divided by m. Simplify. Just a little mathematical operation there. And we get lambda equals to h divided by square root of 2mk, where k is energy of electron. As discussed by de Broglie, a small particle or lighter particle electron will show wave duality properties. Means electrons can show wave properties. Okay, let's watch this video. So let's say electrons are allowed to pass through the two slits. Observe what happens to the pattern formed on the screen. The pattern formed by electrons is the same that pattern of interference produced by light or wave. So from here we can say particles also can behave as wave properties. In 1927, the presence of wave properties of electrons was confirmed through electron diffraction experiment. Photograph below shows diffraction pattern of electrons through a thin layer of graphite. This pattern resembles the light's diffraction pattern through an aperture. So this confirms the de Broglie's hypothesis. Look at the picture, diffraction pattern of electron through thin layer of graphite, and compare with diffraction pattern of red laser light through an aperture. The pattern shows are identical. So from here, this proves that electron also shows wave property, that is, can be diffracted. This is one example application of de Broglie wavelength, the optical microscope and electron microscope. The de Broglie wavelength of an electron beam is approximately 1000 to 10,000 times shorter compared to wavelength of light. So this properties is very important for higher magnification of electron microscope. As you can see, the image of a blood cell using the electron microscope is greater times bigger compared to optical microscope, because the magnification is higher if we use electron microscope. This one best explained by using the de Broglie wavelength formula. Lambda equals to h divided by mv. If the mass of particle is bigger, due to the smaller value of Planck constant, if m is larger, this one will cause the value of lambda to become very small and cannot be detected. That's the reason why de Broglie hypothesis cannot prove the larger particles, like in case of marble, to act like a wave. So this one is just for a lighter mass of particle, like electron, protons or neutron. According to de Broglie, electrons are said to have wave-particle duality. because they exhibit the properties of both particles and waves. Light also possesses both wave and particle properties. Therefore, light and electron are said to have wave-particle duality. The duality is also found in all kinds of radiation in the electromagnetic wave spectrum as well as The duality is also found in all kinds of radiation in the electromagnetic wave spectrum, as well as in subatomic particles like protons and neutrons. Light energy E is transmitted in energy packets known as photon. Energy of photon E equals to hf. From the formula of C equals to F lambda, frequency equals to C divided by lambda. Thus, energy of photon also equals to hc divided by lambda, as we discussed in the examples before. Energy of one photon E is equals to hf. Because of energy of light is in form of discrete or energy packets, thus we can count the photons as 1, 2, 3, 4 and so on is discrete value. Assuming that n photons are being emitted per second, the photons power P, which is the total energy transferred per second, is P equals to NHF equals to NHC divided by lambda. Thus we get one more formula, power equals to NHC divided by lambda. Let's look at how we produce the formula of power. From the energy of photon E equals to hf, this is energy of a photon, means one photon energy. Capital N is number of photons. Thus, the total energy of photons is equals to number of photons multiply hf. When we discuss about rate of energy of photon transferred, means E divided by T. Thus, both sides divide by T and hf divided by T. E divided by T is known as power. Number of photons divided by T is equals to number of photons per second, that defined as symbol n, small n. Thus we get P equals to NHF. So power can be determined by using the formula P equals to NHF. If you substitute C divided by lambda, so you will get the formula P equals to NHC divided by lambda. Let's look at problem solving for photons, energy and power. Example 1. A 50-watt lamp emits red light with wavelength lambda equals to 7 times 10 to the power of -7 meter. What is the number of photons emitted per second? Means need to determine the value of small n. From the formula of power, P equals to NHC divided by lambda. Substitute N equals to P lambda divided by HC. To substitute the value of power, wavelength must be in meter. Sometimes given a nanometer, so you need to change to meter. Planck constant and speed of light. Use calculator to calculate. You will get 1.76 times 10 to the power of 20 second to the power 1 because it is number per second, number of photon per second. Example 2. A red laser pen emits light with wavelength of 670 nanometer. If the number of photons emitted is 3.37 times 10 to the power of 18 per second, what is the output power of laser pen? Means we need to determine the value of P. From the formula of power, P equals to NHC divided by lambda. Substitute the value of N, H, C and lambda. Don't forget the wavelength 670 nanometer changed to meter. So we get is 1.00 watt. Example 3. Assuming that 10% of the output power of a 100 watt bulb is used to emit 2.92 times 10 to the power of 18 photons per second, what is the average wavelength of the light in nanometer? First, calculate the 10% of the power is equals to 10 watt. N equals to 2.92 times 10 to the power of 19 second to the power negative 1. Find the value of lambda. Using the formula of power, P equals to NHC divided by lambda. Thus, lambda equals to NHC divided by P. Substitute the value of N, Planck constant, speed of light, and power. We get the answer is 5.81 times 10 to the power of negative 7 meter. Convert to nanometer. Divide by 10 to the power of negative 9. Because nano is equals to 10 to the power of negative 9. Thus we get 5.81 times 10 to the power of 2, which equals to 581 nanometer. That's all my video today. I will continue in my next video 7.2 photoelectric effect. Thank you for watching. Bye.